Hello everyone, we are Team 4 and will be discussing about the design of a flash drum. In chemical engineering, separation processes are at the heart of industrial operation, and the most common used equipment is a flash drum. A flash drum is also known as a flash separator, which is a horizontal or vertical vessel which is used for separation of vapor-liquid mixture into its individual phases. The principle behind the working of this equipment is partial vaporization or partial condensation, where a slight change in temperature and pressure vaporizes a mixture and condenses the other. Flash drum is a critical component used in units like distillation column, refineries, and natural processing plants. They help in reducing downstream load, recovering of valuable vapors, and improving process efficiency. In this video, we'll be exploring how to design a flash drum, the critical parameters involved in designing it, and how each decision can impact the efficiency of the process.
So, what exactly are flash drums? They serve one essential purpose: separating vapor and liquid phases through a controlled pressure drop. The principle is simple. When high pressure liquid suddenly encounters lower pressure, it partially vaporizes or flashes.
A flash drum is a cylindrical pressure vessel and it has key components working together. For example, the inlet nozzle which controls the pressure drops, the demister pads which remove the liquid droplets, and the vortex breakers which prevent gas entrainment. And the materials for construction of these flash drums vary from carbon steel for general applications to exotic alloys for extreme conditions.
Flash drums come in two main configurations: vertical drums, which excel with high vapor rates and smaller footprints, and horizontal drums, which provide superior separation distance and work when height is restricted. Selection depends on the vapor to liquid ratio and, of course, space constraints.
Now, for how the flash processes work. The high pressure liquids experience a sudden pressure drop, causing partial vaporization. The vapor phase becomes enriched in volatile components and rises, while the liquid phase becomes enriched in heavy components and settles. The system eventually reaches a vapor liquid equilibrium. The design mathematics starts with the material balance, which is F equals to P plus L. We also have our component balance and energy balance along with the mole fraction constraints. So, the challenge is we have 5 equations but 7 variables. Now, going by the rules of degrees of freedom, we know that we need exactly 2 specifications to solve this system completely.
The Rashburg-Rice equation is the mathematical equation required for all flash calculations. This equation cannot be solved analytically, so we use the Newton-Raphson method or any other numerical method for convergence. Once we determine the vapor fraction, we calculate all steel compositions one after another.
Sizing uses the Sawdust-Brown equation for maximum vapor velocity. The K factor is crucial. Also, as you can see, the K factor is 0.11 with demister pads and only 0.03 without them. This is why demister pads are always included. We then calculate area and diameter systematically.
Design standards. Proper design requires compliance with multiple standards: ASME for pressure vessels, API for petroleum applications. Critical parameters include residence time, demister sizing, and pressure relief systems. Safety considerations are paramount throughout. Applications of flash drum. Flash drums are everywhere: petroleum refining, chemical processing, pharmaceutical manufacturing, and utility systems. Design ranges span from half-meter to 6-meter diameters with lengths up to 30 meters. This versatility explains their ubiquity.